We're going to have a look at the idea behind differentiation and what it actually means. Differentiation is a way of finding the gradient of a curve at a certain point. Now, we've done gradients of lines before, but that was fairly straightforward, as at every point that line has exactly the same gradient. So we're going to have a look at this curve and think, well, how could we get the gradient of the curve at this exact point, point A? We're going to do that by looking at what happens to the approximation. So we're going to use an example. We're going to say that this is the curve y equals x squared. We'll have a nice simple one to start. And let's just look at the gradient at this particular point. And we're going to say that this is the point A, and we'll call that 1. So if it has an x-coordinate of 1, it has a y-coordinate of 1. Okay, so we want to find the gradient of the curve at this point. So what we're going to do is we're going to imagine that we add some amount on to our x value. So let's call this extra bit that we add our h. So we're going to add h onto our x value. In this first example, we'll have h as 1. So point B will be 2, because I've added 1 to my x value. But now, as x is 2, y will become 4. 2 squared. Okay, so we can take the gradient of this chord as an approximation to its gradient there. We can see that it's not a very good approximation, as there's a big difference between this gradient, if I continued it, and the gradient of the tangent to the curve at that point. Okay, so let's just do it as a first approximation. So looking at this, we're going to have a change in y of 3. So let's call this delta y over delta x. So it's a big change in y over a big change in x. And that's going to give us 3 over 1. So our first approximation, we could say, well, we think the gradient there is about 3. Okay, about 3. We're suggesting that it's probably going to be a bit less than that, because it's a less steep gradient. How could we improve that estimate? We could have a look at perhaps decreasing our h, decreasing that bit that we add to the x value. So now let's say that I have h as, let's say, a half. Okay, so if I increase x by half, that's going to move this point now to, why did I rub that out? 1.5, and then 1.5 squared is 2.25. So let's see what our change in y over change in x is. So delta y over delta x. That's going to give us 1.25, our change in y, and our change in x was 0.5. Dividing by half is the same as doubling, 2.5. Okay, so we can see, yes, it decreased the gradient a little bit, and there's less daylight now between our chord and our curve. So that's a better approximation. What happens if we make our chord even smaller? So we increase our x by even less. Let's have a look at setting h to 0.1. Okay, so we're getting very close now. So our point D will be 1.1, and our y will be 1.1 squared, which will be 1.21. Okay, let's have a look at our delta y over delta x, and that's going to be 0.21 over 0.1, which is 2.1. So you see there's very little difference between our actual gradient of the curve and the gradient of our chord there. I know this isn't the best drawing. If you want to see a better example of this, please use the GeoGebra file attached, and then you can move the points as close as you want, and you'll see that the gradient gets closer and closer to the value that you can kind of see it's getting closer to here. It's getting closer to 2. And that is in fact the gradient at that point. But how do we know that 2 is the exact gradient? How do I know that this isn't converging to, say, 2.00000468? Because I'd have to get very, very close. How do I know it's not that? Well, let's have a look at generalising this idea. So let's just clear this board. And let's just get ourselves a sketch. Similar again. And we're going to assume that I'm really zoomed in now. Okay, so we've got our point A, and then our point up here, point B. And what we're going to do, like we said before, we add some H. Let's have a general start point. And then I'm going to add some value H onto my X. So this value here will now be X plus H. Meaning that my Y value, remember we're working very generally now, so it's just X plus H squared. I can't say any more than that. I'm working in the most general case possible. I'm just saying it's X plus a little bit, and then due to the function I'm looking at, I square this. Okay, so we're going to use a different letter. So this is lowercase delta. This is just representing a small change in Y over a small change in X. We're assuming H is quite small now to get us a good approximation. Okay, so our change in Y, that's going to be, in fact I can replace that Y with X squared, as I know Y is X squared. So our change in Y is the Y value up here, minus the Y value here. And I divide that by the change in X. Well, I know my change in X. By design, it was H. Cool. So now let's just see if this will simplify to give us more of a clue what's going on. Expanding my bracket. And then tidying up. My X squared cancels with my X squared. And once I've done that, everything has a factor of H in it, so they will cancel out. 2X plus H. And now comes the clever bit. We saw before that the approximation got better as H got smaller. So what we're going to do is we're going to look at the limit as H tends towards 0. So if H goes to 0, what does this become? Well, if H goes to 0, that term is just going to disappear. And I'll be left with 2X. Importantly, and quite subtly, we don't let H equal 0, as then we would not have a chord. We'd be finding the gradient between a point and exactly the same point. But we can see what happens as H gets close to 0. Okay, so that is our 2X. That is our gradient. The only thing we do is, because now we have some almost imperceptible difference, we refer to this as dy dx. So changing our delta, lowercase delta, for a small change in y and small change in x, dy dx means that limit. That is the gradient of the curve y equals x squared. Okay? So at any point on the graph, the gradient of y equals x squared, its gradient, we call this the derivative or gradient function, is 2x. That means if we look at our previous example, we were looking at the gradient at the point where x equaled 1. Plug in x equals 1 into here, we get dy dx is 2, the limit we predicted it was going towards. In the GeoGebra file attached, you can change the function here and you can see what value it goes to. You can also change the point at which you're estimating the gradient. What I'd like you to do, try and find a similar kind of process to the one that we've applied here, but try applying it to a different function. So maybe try it with x cubed, or y equals 3x squared plus 2x. See if you can apply exactly the same ideas to figure out the gradient of these graphs. Once you've done x cubed, maybe you could try y equals x to the 4. See if you can spot some kind of general pattern and understand why it works using this process. Thank you.